This is the last lecture video for Chapter 17, the additional aspects of aqueous equilibrium. So up until now, everything's been acid-base. It's very much been a continuation of Chapter 16. Starting here, this is where the additional aspects come in. So it's what else does equilibrium impact other than acids and bases? The good news is we're not learning new math skills. We know everything we need to know about equilibrium. We know about equilibrium constants. We know about ice tables. We know how to handle acids and bases now. So we're just going to throw in what are other things that go to equilibrium and practice solving them. The only thing that's going to show up here that's maybe been a little bit. So back in Chapter 15, when we first learned about equilibrium, we had lots of equations that when they were balanced, they had coefficients other than 1. So like a coefficient of 2 or a coefficient of 3. We just haven't seen that in a while. In Chapter 16, everything was a 1 to 1 to 1 to 1 mole ratio. And in Chapter 17, everything so far has been a 1 to 1 to 1 to 1 mole ratio. But now that we're back at these additional aspects, we're going to go back to equations that are not necessarily a 1 to 1 to 1 to 1 mole ratio. So just a quick reminder, when you have a coefficient, a whole number, in front of a compound or an ion, in terms of where that is impacted in the equilibrium constant, well, that becomes the power. It's raised to that power in the equilibrium constant expression. So when that products over reactants equals K, if it's got a 2 in front of it, it's now squared. It also impacts in the ice table when we're doing the plus or minus the X in the change row. So whatever the coefficient, that is the number of X's that goes into the change row. So again, we've already done this. It's just been a little bit and a reminder. And so we're going to do some more examples. Like, we're going to practice this, but just some things that you already know that you maybe haven't had to use in a while. So in this last part of Chapter 17, the textbook goes through several different examples of things that also undergo equilibrium. The one that I'm focusing on is the solubility product. That's the one that's in the title of this. We're going to mention I'm going to mention a couple others, but solubility product is the one for you to really know. Because at the end of the day, I kind of feel like if you can handle solubility product, which is just equilibrium, you can handle any other random equilibrium thing that happens. So, anyway. Okay, so solubility product is our focus. So this, before you have a panic attack, these are the solubility rules. You learned about them in General Chemistry 1. You were supposed to have memorized them in General Chemistry 1. But again, before you have a panic attack, you are not memorizing these solubility rules now. I just wanted to remind you that you've seen these before, what they are, and most of this little video is going to be, oh yeah, and by the way, those solubility rules, they were kind of crap. So this table was supposed to tell you if you take an ionic compound and if you add it to water, will it dissolve, yes or no? So the point of the solubility rules were to tell you yes or no, they dissolve. If it was soluble, we wrote aqueous next to it in a balanced equation. If it was insoluble, it did not dissolve, and we wrote solid, S, next to it in a balanced equation. That's when you used these. So when you were first predicting products, you had to write your own chemical reactions, like the products, and to know if you put solid or aqueous, we used the solubility rules. So these were, wrong is the wrong term. They're an oversimplification. So it turns out that every ionic compound dissolves in water. It's just how well it dissolves in water. So the solubility rules are dividing ionic compounds into basically the same equivalent of us taking acids and calling some of them strong acids and the rest of them weak acids. That's exactly what it's doing. The solubility rules, if according to the solubility rules something is soluble, it's like a strong acid. It's soluble and it dissociates 100%. If according to the solubility rules something is insoluble, again, that's an oversimplification. So what really happens is it dissolves, but it goes to equilibrium. It has an equilibrium constant. So we're not going to worry about in Chapter 17 all the soluble ionic compounds because there's nothing fancy to do with them. They dissolve in water. They dissociate completely. Everything you needed to know about them you learned in Chapter 4 of Gen Chem 1, which is if it's soluble, it breaks into its positive charge and negative charge, and that's how it lives. If it's insoluble, though, it goes to equilibrium. That's what we're going to focus on. So in Chapter 17, if you see an ionic compound in equilibrium stuff, it's all going to be based on the solubility rules. They would have called it insoluble, but in real life it will dissolve. We just have to calculate how much of it will dissolve. So they all have their own solubility equilibrium constants. Okay, so solubility products are what we call the ionic compounds that, according to the solubility rules, are insoluble. And what we've learned is that they actually go to equilibrium. Okay, so this is an example of barium sulfate. Barium sulfate, according to the solubility rules, is insoluble. In real life, barium sulfate solid dissociates, it goes to equilibrium, breaking into its barium ion and its sulfate ion. This is the general pattern for solubility products. You're going to start on the reactant is going to be the solid. The ionic compound is a solid. Then you're going to write in the equilibrium arrows, and then you're going to write the cation, the positive charge, and the anion, the negative charge. Both of those will be aqueous. And then you have to make sure it's balanced. So in this case, it's a 1 to 1 to 1, but that's not necessarily always the case. So we can write the equilibrium constant expression for this. So looking at that equation, backtracking here, this buddy's a solid. So we're going to say that it's equal to 1, or we're going to ignore it. This is aqueous and this is aqueous, so those are going to be part of the equilibrium constant expression. So products on this side over reactants, well, the reactants is just going to be equal to 1. So the equilibrium constant expression, barium times sulfate over 1. Okay, so in chapter 16 and 17, with acids, we called the equilibrium constants Kas. With bases, they were Kbs. For ionic compounds, it is KSP, where SP stands for solubility product. That's just what they called them. Okay. So here's the general pattern. You're going to start with the ionic compound, and it's going to be written on the left, and with a solid next to it. Then you're going to write your equilibrium arrows. Then you're going to write the cation, which is the positive charge from the ionic compound, plus the anion, which is the negative charge from the ionic compound. You will show the charge. So cations are going to always have a positive. The reason why I wrote X there, I don't know what charge it is. It's going to depend on what the compound or the ion is. And then anion, same thing. It's going to be something negative. The M and the N are the coefficients. When you balance the equation, what are those? So the solubility product expression will be equal to the cation raised to whatever the coefficient is, power, times the anion raised to whatever the coefficient power is. And then it would be over 1, because the ionic compound is a solid, so I'm not even going to write that. Just always make sure that it's balanced before you worry about this. Another thing that we're going to see as we do our calculations, the questions are going to not be asking about pH, like the questions were earlier in this chapter, in chapter 16. The questions could be asking you to solve for the solubility equilibrium constant, the solubility product constant, the KSP, so that's one way. The other way the questions are going to ask, they're going to ask you to solve for the molar solubility, or they're just going to use the word solubility. And what that means for us is that's the value X from the ice table. So once we set up our ice table, whatever X is equal to, that is the molar solubility. So with these solubility product questions, I'm going to ask you the question one of two ways. Either solve for the KSP or solve for the molar solubility. Molar solubility means X, KSP means the equilibrium constant. Okay. So this is going to be, I'm going to make up some solids, and we're going to practice writing the equilibrium, like the equilibrium equation, and then the KSP expression. So I didn't plan for this, so I'm just going to make up some stuff. Let's go with, I have an idea. Magnesium fluoride, which is the one we're going to be doing the lab over. So magnesium fluoride. So you are going to have to remember some things. Sometimes these are going to be given to you by their ionic compound, like by the name. So the naming rules are things you may have to remember. You're going to have to remember by looking at the periodic table what charges different ions have. So if you have questions over that, just let me know. Or refer back in our textbook to chapter 2. That's when all this stuff happened. As long as you have any version of our textbook, you can go back to chapter 2, even though it's not something that's covered in this class. It's in the e-text, it's in the paper text. Chapter 2 is your friend. Okay, so anyway, we're following this pattern. First, we write the ionic compound as a solid. Check. Write the equilibrium arrows. And then we're going to write the positive charged ion plus negative charged ion. So positive charged ion is magnesium. If you look at magnesium on the periodic table, it's in group 2, which means it's a 2+. The ions are always going to be aqueous. Okay. Plus, and then the negative charge is fluoride, which I look at the periodic table in group 17, it's a -1, aqueous. If I look at this equation is not balanced. I have 1 magnesium on each side. I have 2 fluorines on the left and only 1 fluorine on the right. So I'd have to put a 2 right there. So if I'm writing the KSP equation, products over reactants, it'll be magnesium times fluoride, where fluoride is squared. One thing to be careful of, the charges aren't the powers. That's just, really, it's just the charge. Let's do aluminum sulfate is my solid. Okay, so aluminum sulfate's my solid, equilibrium arrows, then it's got aluminum ion, which is a 3+ charge because it's in group 13, and a sulfate ion, which is a -2 because it's a polyatomic ion, and that's what sulfate is. If we look at this, it is not balanced, so I'd have a 2 there and a 3 there. So my KSP equation would be products over reactants, so aluminum ion squared times sulfate ion cubed over 1 because it's a solid. So that's the pattern. So the reason why I'm telling you the pattern is in these questions, the equation's not going to be given to you. The question's just going to tell you what the solid is. And then you're going to be expected to take the solid and write it as an equation like this. Okay. So just some clarifications. KSP is not the same thing as solubility. KSP is the equilibrium constant. That's all it is. It's an equilibrium constant. The solubility is, like I said, for us, it's typically going to be equal to X from the ice table, which would then have the units of molarity because ice tables are in molarity. The questions could go on and then ask you for it in grams per liter, which would just mean you would have to convert moles per liter, which is molarity. If the question wants you to do to grams per liter, then you're just going to use the molar mass and do a unit conversion to convert back and forth between those. Okay, so let's try some questions. So this one, I'm starting out nice and tricky. I gave you the name of the ionic compound. So we're going to have to first go from name to symbol, and then we'll have to write the equation. So solid silver chromate is added to pure water at 25 degrees Celsius with some solid undissolved. Okay, so that means we have both solid and aqueous things. That's why that's mentioned. The system is allowed to achieve equilibrium. After being tested, the silver ion concentration was found to be 1.3 times 10 to the -4th molarity. Calculate the KSP. Okay, so first our job is to take the name silver chromate and come up with the formula for that. So silver, do we remember the element symbol for silver? Well, it's Ag. Okay, and then we need to think of the charge. If you look at your periodic table, silver's in the transition metal section. So you would probably expect it to say silver something in parentheses charge, but silver is one of the weird transition metals. It always has the same charge. Silver is always +1. Chromate is a polyatomic ion. It is Cr(O4) with a charge of -2. So silver chromate solid, we have to put these ions together so the charges cancel. Right now the cation has a +1, the anion has a -2. One of each isn't going to work. Silver chromate is Ag2Cr(O4). That's the ionic compound. So I'm going to go ahead and set out the equation. So it's going to be the positive charge, which is silver, aqueous, and the negative charge, which is chromate, aqueous. I look at this, it is not balanced. I'm going to put a 2 right there. So the question wants us to solve for KSP. So just for, I'm going to write it up at the top because I know I'm going to need space underneath here. So I'm going to write the KSP expression. Products over reactants. So silver squared, because of the 2, times chromate to the first power over 1. So I'm not even going to write the 1. So we're trying to solve for KSP. So what we need is we need the equilibrium concentration of silver to put in there and the equilibrium concentration of chromate to put in there, and then we can solve for KSP. Looking at the question, we were given one number. We were given the equilibrium concentration of silver. We don't have the chromate. So since we don't have everything we need, we are going to have to do an ice table. So when we do an ice table, do you remember what we do to solids and liquids? Well, we ignore them in the equilibrium constant expression, so we ignore them in the ice table. So that's going to be true here as well. You're going to get to ignore the solid every time. Reading the question, I do not believe we were given any initial information, so I'm going to write a 0 and a 0. We were given equilibrium information for silver, so 1.3 times 10 to the -4th goes right there. So I'm going to fill out the change row. Well, this has to be the plus side because we started with zeros. So this will be plus x. This will be plus 2x. So here's another time. It's been a while since we've had a coefficient, so 2x. So I need to solve for chromate. Well, I do have one column that's completed. 0 plus 2x equals 1.3 times 10 to the -4. So I can just do algebra and solve for x, which is 6.5 times 10 to the -5th. Well, chromate is equal to 0 plus x. Okay, so I just said, well, x is 6.5 times 10 to the negative fifth. So I now have the equilibrium number for silver and the equilibrium number for chromate. So I'm going to take my KSP expression, type in 1.3 times 10 to the negative fourth for silver. I'm going to have to square that, times 6.5 times 10 to the negative fifth for chromate. I'm going to grab my calculator, plug that in, and what I get is 1.1 times 10 to the negative 12th. So that is how we can solve for the KSP value. Hopefully we're feeling okay with the ice table setup. Yeah, hopefully. I'd like feedback, but I can't ask you for feedback right now. All right, we're going to do another one. This time we're going to solve for the solubility instead of the KSP. So in the question, the KSP for lanthanum 3 fluoride is 2 times 10 to the negative 19th. So we were told the KSP value. What is the solubility of LaF3 in water in the unit moles per liter? So solubility or molar solubility, come on, nope, okay, is equal to X. So what they're saying is do the ice table, solve for X. So first we have to write our equation. So LaF3 is the solid. Arrow, arrow. La, which will have a 3 plus charge, which I know that because there are 3 fluorines, and fluorine is a -1. So I'm going to do this. So we're supposed to solve for KSP. Well, the KSP equation, products over reactants, equals La3 plus to the first power times fluoride cubed. So to solve for KSP, or actually no, sorry, we have KSP, we need to solve for X. Well, I can plug the KSP number in, but I don't have the La or the F minus molarities or anything to solve for X, so I'm going to go ahead and set up my ice table. The solid, well, it's a solid, so I can ignore it. We were not given any initial numbers. I'm going to start with 0. This is going to be plus X. This one's going to be plus 3X. At equilibrium, I don't have any numbers, so that way I'm just going to bring down this is X and this is 3X. So I don't have any values, so what I'm going to have to do is do 2 times 10 to the negative 19th. What I'm doing, I'm plugging into the KSP equation. That is X, and then it's going to be the quantity 3X cubed, which 3 cubed is 27, and then X cubed times X is X to the 4th. So now I just have to do some algebra to solve for X. So I'm going to divide both sides by 27, and then I'm going to have to take it to the 1/4 power, and when I do that, I really only have one significant figure here because of the KSP. For X, I got 9 times 10 to the negative 6th. Since X is coming from the ice table, it's in the unit molarity. So that is the answer to that question. Just the solubility means solve for X. We just solved for X, 9 times 10 to the negative 6th molarity. So another thing from chapter 15, a blast from the past that we talked about, used it in chapter 15 and then haven't really dealt with it much since then, is the solubility, or the product quotient. Sorry, I'm having issues. So Q is I call it the right now constant. So K is the equilibrium constant. We can only plug equilibrium numbers into the equilibrium constant expression. It tells you what the ratio of products to reactants is at equilibrium for that specific reaction. But Q is if I wanted to know what is the ratio of products to reactants at any time, we dealt with that. So Q is the right now, K is the equilibrium. The only time when we know that right now is at equilibrium is when the number I get for Q is equal to the number that we were given for K. So when Q equals K, in chapter 15 we said, oh, it's at equilibrium. Okay. All I'm adding here is, when we're talking about solubility product, the other word they could use instead of equilibrium is saturated. So saturated is actually not a new word for us this semester. We talked about saturated back in chapter 13, which is when you're dissolving the solid and it's dissolved as much as it can. So it's full. Okay. Unsaturated was when there's less than that, and then supersaturated was the super cool one. So when Q equals K, it's at equilibrium, but another word that might show up is saturated. When Q is less than K, so just a reminder that Q and K are both equal to products over reactants. So if Q is less than K, so for example, if Q is 12 and K is 6,000, well then I can very clearly say that right now, which is what the Q is telling me, is not at equilibrium, which is what the K is telling me. Q is too small, it needs to get bigger. So if we look at this ratio, if I want to make Q bigger, Q needs to go from 12 to 6,000. Then based on this ratio, I need more products and less reactants. Okay? So we said back in chapter 15 that we would make more products, which was also shift to the right. Okay. Well, if we're thinking about how that applies in this specific situation with solubility product, products are the things that are dissolved. So making more products or shifting right is the same thing as making the solid dissolve, making more aqueous things. Okay. So in the opposite situation, if I have a Q value that is large, so like 32, and my K value is 0.11, so Q is what's happening right now, K is what's happening at equilibrium. We can very clearly say that right now is not at equilibrium. So if I need to make the Q equal the K, I need to make the Q smaller. So if we come back up here and look at our ratio, well, to make the Q smaller, I need more reactants and fewer products. So more reactants, which means shift left. Those were the words that we used. But when we're applying this to solids, well, we're shifting left, we're making more reactants. That's the product, or that's the solid. So we're making more solid. The solid's also called the precipitate. So if we're making more solid, it's going to precipitate. Solid is going to show up. So Q and K hasn't changed from chapter 15. We haven't seen it in a while. But all I wanted to do on this slide was remind you of Q and K, but also include the words that we're going to see, things like saturated, dissolve, and precipitate, which mean the same thing as more products shift right, more reactants shift left, or equilibrium, but you're going to see them in chapter 17, and I don't want that to throw you off. Okay, so continuing on with things we've talked about before, the common ion effect is just the Le Chatelier principle, which pretty much is if it's at equilibrium and then we add something to it, how is the reaction going to respond? This is when the answers again are shift left or shift right, more products, more reactants. So if we looked at this reaction, and if I were to add more barium, how would this reaction shift? Well, if I add more barium, the reaction's response is it's got to get rid of the barium. So to get rid of the barium, it would shift to the left to use up the extra barium. So it would shift to the left, which would make, so I'm going to write left, make more reactants. And in terms of the solid, we need to think about this in terms of the solid. So if I added more barium, will this make the solid dissolve more or dissolve less? Well, when I added the barium, it shifted to the left. When it shifts to the left, that makes more solid. So there's going to be less that dissolves, because instead of dissolving, it's going to turn back into the solid. So we're going to decrease the solubility. So it's still the Le Chatelier principle, but we're looking at it from the point of view of solubility. So if we're shifting to the left, it's going to decrease solubility. If it's shifting to the right, that means make more products. That means more will dissolve. So that's going to increase solubility. So conceptually, hopefully we're feeling okay with that. If you need to go back to chapter 15 and check out the Le Chatelier principle, then do it. What I want us to do now is let's practice some calculations with this. So, you know, what's going to change if we have a common ion effect? If we added more barium, what is the calculation? What are they going to look like? So this is a real life example. This one, so in real life, if you're going to have an x-ray done for your intestinal stuff, they're going to ask you to drink a suspension of barium sulfate. So it's a suspension because the barium sulfate is insoluble, very little of it dissolves, so mostly it's a bunch of solid mixed with a bunch of water. The issue is barium ion is toxic, so it can kill you. We need to calculate the molar solubility, which is X, of barium sulfate. So what I want to know is basically. The molar solubility is X. It's also going to be the amount of barium. I want us to calculate how much barium is going to dissolve and go into your body, this toxic barium, when you drink this barium sulfate suspension. So this is, anytime we have a KSP, you know it's a solubility product. So our equation is going to look the same. We're going to start with the solid, equilibrium arrows, positive charge, negative charge. So barium sulfate is the solid, equilibrium arrows. Barium is the positive charge. I'm going to write 2 plus. Sulfate is the negative charge. It's a 2 minus. And the KSP expression, barium KSP is equal to the barium ion times the sulfate ion. Both of them have coefficients of 1, so they're not raised to another power. So we want to calculate the molar solubility, which is X. So I'm going to do the isotable. So solid I get to ignore. We were not given any initial, so I'm going to say 0. Then I'm going to write plus X. This is equal to X. This is equal to X. I need to solve for X, so I'm going to plug 1.1 times 10 to the negative 10th into KSP. X in for barium, X in for sulfate, which X times X is X squared. So I'm going to square root both sides. And when I do that, I get 1.0 times 10 to the negative 5th is equal to X. So that's the molar solubility. In other words, the barium ion, because I don't care about the sulfate so much, but the barium ion is going to have a 1.0 times 10 to the negative 5th molarity. Okay, so that's how much barium would dissolve in your body. I don't have on the top of my head, usually I've looked this up, but I forgot to, what the amount of barium it is in your body before it's toxic, before you die. Okay, so let's look at another scenario. I'm going to say we're going to add a 0.10 molarity solution of sodium nitrate to this barium sulfate slushy and drink it. I want us to calculate the molar solubility of barium sulfate, which is X again. In this scenario, the KSP for barium sulfate is 1.1 times 10 to the negative 10th. So what's different, what's going on here, is we have two compounds. We've got barium sulfate and sodium sulfate. Well, if we're talking about solubility product, the equation is always solid on the left, equilibrium arrows, positive charge, negative charge. So to figure that out, you're going to go with the thing that we're solving for, barium sulfate. That's going to be the equation that we write. So the equation is actually going to look exactly like the last one. Barium sulfate solid, equilibrium arrow, barium ion, aqueous, sulfate ion, aqueous. The KSP expression is still barium times sulfate. Okay, so you're looking at this and you're like, but there's no sodium sulfate in there at all. You're right. The sodium is not important at all in this equation. The sodium sulfate, what it is it's adding an amount of sulfate. Sodium sulfate, sodium's not part of this equation, so we don't care. Instead, we just care about the common ion, the ion in common. The ion in common between sodium sulfate and barium sulfate is sulfate. So how that's going to play into this, when I go to set up my ice table, I ignored my solid. There's no barium, but there is going to be an initial amount of sulfate, the 0.10 molarity coming from the sodium sulfate. So now I'm just going to do my ice table. I just have an initial value. Okay, so now if I'm going to go plug this in to the KSP expression, if we look at the KSP value, it's negative 10. So I'm just mentioning this because if I'm looking at the shortcut idea. So negative 10, well, the equilibrium constant is negative 8, negative 9, negative 10, negative 11, negative 12. We can use the shortcut, which means I can get rid of trailing x's, which that plus x after the 0.10 is a trailing x. What that lets me do, plug this in for KSP, plug x in for barium, plug 0.10 in for sulfate. I've got to do a little bit of math here. And when I do my little bit of math, I get 1.1 times 10 to the negative 9th as the molarity. Okay, so that's the molar solubility of barium. If we added sodium sulfate to this, so what happens is 1.1 times 10 to the negative 9 is way smaller than 1.0 times 10 to the negative 5th. So if we added that sodium sulfate, you're getting less barium dissolved in your body. so it's less toxic. Okay? We're going to do one more example that has a common ion. But the thing that I don't want you to do, and I almost don't even want to show you what I don't want you to do, because I don't want you to be like, oh, I've seen that before, so I'm going to do that. This is what people try to do with this problem. They take sodium sulfate, and they react it with barium sulfate. And then they do some kind of arrow, and then they predict their products. This is where hopefully you'd be like, hey, something's not right here. So sodium is going to hang out with sulfate. So on the other side, sodium sulfate. Barium is going to hang out with sulfate, so barium sulfate. If you look at this equation, nothing happened. So you wouldn't really know what to do with this. And then sometimes people are like, ooh, then I'm going to make up my own made up, I don't know, just, oops.